Be here. I'm Yuna from the Electrical Engineering in Gwangwon University, and our professor is Singho Song. Today, I'd like to introduce you to our project, Bidirectional DC-DC converter design for charging and discharging batteries. Our table of contents consists of the following order. First, topic and objective. Our model is bidirectional DC-DC converter hardware. Bidirectional converters can be used in regenerative braking systems, such as electric vessels, and it is possible to increase the efficiency of battery by boosting low voltage battery and transferring it to the load. And our specific goal is to make 100 watt 3-phase bidirectional DC-DC converter hardware. Also, based on the target watt, LV voltage and HV voltage were selected as 12.8 volt, 30 volt respectively. And this is our final product. First is the oscilloscope and power supply. Second is the battery and load. Third is the 3-phase bidirectional converter. And fourth is the DSP, which can control the 3-phase duty. And finally is the IPM, which can perform switching operations. Next, experimental results in 3-phase converter action waveform. We increased the duty ratio from 0.3 to 0.7. And depending on the inductor voltage, it was possible to confirm that the current was charged and discharged in boost mode and buck mode. And 3-phase input current ripple reduction effect rectification waveform. We selected boost experimental conditions duty as 0.6, ILV as 1 ampere. As compared to the single-phase operation in 30 kHz, the 3-phase in 30 kHz showed a decrease in input current ripple by more than 1/3. Okay. And next, boost PI voltage control waveform observation. Boost output voltage target as 30 volt, input voltage was changed by 12 volt reference plus minus 1 volt. As a result, it was confirmed that the output voltage remained constant at 30 volt through the PI control, which can adjust the PWM duty cycle even when the input voltage changes. In the same manner, in both PI voltage control waveform observation, output voltage remained constant at 12.8 volt through the PI control even when the input voltage changed. Also, load variation test. We observed load variation in boost mode. Boost output voltage target 30 volt, input voltage of battery 13.02 volt. When load changes were given like that, overshoots came in at 15%, 30.5%, and 30.2% respectively. Also, response times were 20 millisec, 4 millisec, and 4 millisec respectively. So this is our HV current ripple variation in overshoot. And in troubleshooting, first, variable PI gain control for boost mode non-linearity relief. The graph on the left shows the output voltage according to the duty ratio in boost mode, which has a non-linear characteristic. So, in systems with large load fluctuation rate, the boost converter with linear PI control is hard to guarantee the target response time for the entire load segment. In that case, we solved the output voltage variation rate by duty ratio and multiplied it by Kp constant and Ki constant. As a result, response speed and input current ripple in over duty ratio spectrum could be improved. And this graph shows before and after applying the variable PI gain control. The graph on the left represents the application before and after the graph on the right. Specifically, in simulation, by using PI gain compensation, we've achieved 30% enhancement of voltage response time and input current ripple as compared with previous PI control. Also, current sensing method for ADC. When the inductor current is in continuous mode, it is possible to execute ADC at the average value of the inductor current by setting the timer interrupt point of the DSP at the rising value of the PWM carrier. However, when the inductor current is in discontinuous mode, it is impossible to run ADC at the average value of the inductor current. So, current gain feed-forward compensation was introduced to calculate the ratio of the actual travel time to the total cycle. And troubleshooting in current imbalance improvement. We selected boost output voltage as 30 volt, input voltage of battery 13.02 volt. When we only use voltage PI control, a current imbalance occurred because of the error of inductance installed on each wire's inductors. So, three-phase inductor current imbalance rate was 23.6%. But by using voltage current dependent control and reducing parasitic component as same wire length, the three-phase imbalance rate could be resolved from 23.6% to 1.44%. And troubleshooting in HV output voltage ripple. We proceeded with the same conditions as the previous experiment. Because of the switching noise from signal and power source, HV voltage ripple was 2.5 volt, which is the 8.3%. But by separating the signal line and the power line, we can reduce noise. As a result, HV voltage ripple was 0.5 volt, which is the 1.3%. And this is our final spec. Buck and boost bidirectional mode and rated voltage LV 12.8 volt, HV 30 volt. And response time with the millisecond for load fluctuation is 4 to 12 millisecond, and overshoot for load fluctuation is 3 to 15 overshoot. And our switching frequency is 30 kHz. And this is our final results and effect. First, in results, 1/3 reduction effect of current ripple through three-phase interim method, and 22% improvement in imbalance current through voltage current double loop controller design. And finally, boost battery discharging efficiency through boost and buck operation of bidirectional converter. And in effect, we improve the efficiency of all power systems using batteries, and this DC converter allows high voltage and low systems to be handled by low voltage batteries, and extended battery life and reduction passive elements capacity by using three-phase interim method. And at the end of the project, we can use measuring equipments and DSP. So it means that we can know how to handle sensor signal process. So this is our presentation, and thank you for listening.